Well, good afternoon. It's 12:21, actually 6 minutes late getting started. Sorry, for Cal 3. And nobody else is in the room, so I'm going to not wait any longer and start where we left off last time. I do have a few announcements, but I want to wait until somebody's in the room so I don't have to just keep repeating them every time someone comes in. So if by the end of the class, if no one's here, I'll try to remember to make all the announcements then. So hopefully some people will be showing up. So we'll go from current slide. And we've done example 2, but example 3, 4, and 5 were all not given on the slide set. So that's where we left off last time. We're in chapter 14. Which is multiple integration, 14.2, which is double integrals in volume. And we are getting ready to start example 5 at the top of page 985. Let me get my pen set up. And if it'll go, there it goes. All right. So it says find, I'm sorry. I crammed down lunch way too fast, and I'm something stuck in my throat, I think. Okay, find the volume of a solid bounded above by the paraboloid. So z is equal to 1 minus x squared minus y squared. Okay, and below by the plane z is equal to 1 minus y. Okay. Now, they show the figure in the text, which doesn't do us any good because it's not on the slide set. Okay? But this is on top. Okay? And this is below. Okay. Now, what this forms, by the way, is, let's see, a good way to express this. We need to know in a sense, the boundary of this. And since these are both the z's, we set these equal to each other and say 1 minus x squared minus y squared is equal to, because the two z's are the same, 1 minus y. Okay? And then what I would suggest is getting all the x's on one side and the y's on the other. And the choice of which to do is probably get x's by themselves and everything else with the y, because you already got y squareds and y's, and you only have one place where it's x, so let's do x squared. So let's add x squared to both sides, and subtract 1 and add y to both sides. Okay, that goes, that goes, that goes, and that goes. So we have y minus y squared is equal to x squared. Okay? Now, now, if we look at that by itself, I would really be tempted to write that as x squared is equal, wait, that wouldn't work. and I think this might be the better way to do it. I'm going to move this to the other side too. So I'm going to subtract y. I wish I had done what the book had done. Subtract y and add y squared. So this gives us plus y squared minus y, okay, is equal to 0. Okay. Now, let's split that to x squared plus y squared minus y, and what I want to do is complete the square here. Half of minus 1 is negative 1/2. Square that is plus 1/4. Well, I just added plus 1/4 here, so I'm also going to add a 1/4 on this side, okay, to the 0. Now this gives me x squared plus y minus 1/2 squared is equal to 1/4. Okay? Now, this sounds bizarre, but I'm going to divide both sides by 1/4. Okay? Well, sorry. Sorry, I had something hung up on the tooth. I don't think that has to do with the choking, but it still contributes. Okay? Which is multiplying both sides by 4. Okay? So that'd be 4x squared here and 4y squared there. Okay. And that's equal to 1. Now, okay, finally. Finally got that thing off. It was just bugging me like crazy. Okay, I multiply both sides by 4, but in reality, I'm dividing by 1/4 as well, which is 1/2 squared. Now that looks a bit bizarre. The reason I wrote it that way is trying to duplicate this. X squared over a squared plus y minus c squared over b squared. No, make that a b here, and that's still an a squared here, is equal to 1. That is your standard equation for a circle, okay, of radius a and centered on the y-axis, so you're not plus or minus anything, but the y is b above the x-axis, so you have a vertical shift, you might think of, up. Well, what is our problem here? The b is 1/2, and the a's are 1/2, because you're squaring. Okay? So that means we have a radius of 1/2, but also a shift upward of 1/2. So where does that land you? Okay? That is on the coordinate plane here. If the radius is 1/2, the center is up 1/2, so this is 1/2 here, and the radius is 1/2. That gets you to 1 minus 1 plus 1/2 minus 1/2. Here is the circle in the xy plane where that is located. Okay? Now, that's what you're projected over. Okay? And you're going from this z up to that z over that circle. So, I don't know if it really matters whether you do dx's or dy's. They're basically equivalent, but in your, so glad to see you. I hate talking to myself. Okay, Muhammad is here. Okay. And let me actually turn on the projector. All right, good deal, thank you. And I'll light for you. Second. What's that?
I think it's bright enough.
Okay, you don't want the light on. Okay. Well, it might be easy to read paper because of the shadow or something. Okay. All right. The projector is trying to come on. We're in Chapter 14, Multiple Integration, Section 14.2, Double Integrals in Volume. And you don't have a book, do you? Okay. What we have here, this is example 4 in the text on page, example 5 in the text on page 985. And what we have here is an elliptic paraboloid that's opening down, okay? And you have a plane, z is equal to 1 minus y, cutting through that elliptic paraboloid. So the elliptic paraboloid is the top part, and below that is your plane, okay? Now, that's the volume in between that we're trying to determine. Okay, it says, find the volume of the solid region bounded above by the elliptic paraboloid and below by that plane. But what we need to do is find out on the xy plane, which is your base down there. That's not what we're integrating to, but that's where it's coming from. X's and y's, the region that's projected down there. And what we do to do that is set the z's, these are both z's, set them equal to each other. And then I did some various manipulation. The book kind of wound up in a weird spot, and I did some changes to it and got it into the form of x squared plus y squared minus y is equal to 0 when you rearrange this. I went through a couple things. I'm trying to do it the way the book did. And I thought it was so much easier to do it this way. Well, not easier, but it's more illustrative. And that is flicking like crazy, and that's almost enough to give me a headache. Sorry about that. I don't know if my bulb's about to go, or I don't know what to do. But can't help it. So what I did was complete the square here. Take half of -1, that's -1/2, square it, and that gives you a plus 1/4. If I add a fourth here, I have to add a fourth on this side, that side to 0. And then that gave me x squared plus y minus 1/2 squared is equal to 1/4. Well, I want a 1 over there, not a 1/4, and there's a reason for that. So I'm going to multiply by 4 on this side, which makes it a 1, but divide by 1/4 over here, which is the same as multiplying by 4, but make that 1/2 squared, okay? And then what I said was, this is the standard form x squared over a squared plus y minus something squared over b over a squared. If those are the same two numbers here, this is a circle. This is your radius down here, and this is your offset. Well, the radius is 1/2 and the offset is 1/2, and it's 1/2 up, okay? So what that means is you have a circle here centered at 0, 1/2, there it is, and radius of 1/2, which gets you down to 0, over to 1/2, down, up to 1, down. So this is the circle, the basis under which the xy plane, this plane is cutting that parabola, and it projects onto a circle. So this is what we have to be playing around with, and now we have to decide, are we going to do dx's or dy's? And because you have more y's in the problem than you have x's, I would say let's go with the dy. And that's what the book does too. They don't say that's why they chose it, but that's what they're doing. So we're doing little rectangles like this, okay, and integrating that from, and since you're doing dy's, that's going from 0 to 1, okay. This is a 1 up here because this is 1/2 here, and that's 1/2, and this is minus 1/2 here, so that's a plus 1 up there, okay. So that's going to be one of your integrals, okay. Now, since this is the equation for that circle, and we're going to write that slightly differently again. I put it in that form because that was sort of your standard form, but let's go back to this form, which I had written before, but then I erased it. 4x squared plus 4 times y minus 1/2 squared is equal to 1. Okay? Before I moved the 1/2 underneath to show that is indeed the radius. Okay? Guess I could have left it. Well, but anyway. Now, let's solve this for x, which we all, and that's why the book did it the way they did. So let's take this back to being of 1/4 here, okay, and solve for x. So x squared is equal to 1 I'll write it this way to start with. I may change it later. 1/4 minus, get out of there, 1/4 minus y minus 1/2 squared. Okay? Get out of there. Okay? And so your x's are going from I wish this looked better. Sorry. It can be better. Let me erase this. Like I said, the book started it this way, but it wasn't obvious to me, even though I could see it was, that formed the circle. They just said it's a circle. But if you go back to this equation right here, what I did was subtract and add y back here. Go back to this equation here. X squared is equal to y minus y squared. So that means that x is going from minus the square root of y minus y squared to plus the square root of y minus y squared. So you see this value here is the square root of y minus y squared, and this value over here is minus the square root of y minus y squared. So that's what your x's are going between. So that gives you one integration. Your dy's are going from, your dx, right? Your dx's, and this is the part that seems so bizarre here, the way they draw this. Your x's are going between those two values. And what you're doing here, which they don't show, and I wish they did, I thought of this after class last time, you see you're doing a little dx in there as well and integrating from one x to the other x. That's how you get the rectangle, and then you do the y's from 0 to 1. So think in terms of integrals, and that's what you're going to have here. So I've run out of room just setting this thing up. There are my x's going from minus square root of y minus y squared to plus the square root of y squared, square root of y minus y squared. That's what the x's are going between, and then the y's are going from 0 to 1. So let me erase a lot of this stuff, okay? I've already used this, so I'm going to erase it, okay? And this was all sort of scratch work. This was convincing myself it was a circle. I've convinced myself of that, so we're happy with that. So I can erase all this for now. Okay, I'm going to leave my picture here just for illustrative purposes, I think. Okay, and oh, I erased too much. No, I didn't. Okay, that's fine. Okay, so what is our integral? Okay, well, you're doing your dy last, and that's going from... Okay, I said that, but we're going to draw the dy, but we're going to integrate that with dx's, and we have to do that first to get across there, and then we're going to do our dy's. Okay, so the dy ultimately is going 0 to 1, so that's the last one. Before that, we do the dx is going from minus the square root of y minus y squared. And since that's so awkward and it's exactly equivalent, I'm going to make that twice from 0 to the square root of y minus y squared. Okay? So that 2 is in there because I'm just, rather than doing from here to here, I'm going to do twice from here to there. And it's the same thing because my picture doesn't look like it, but it's equivalent on both sides of the y-axis. So I'm going to go twice 0 to the right-hand side. Okay? So that's why the 2 is in there. And then up here is the difference between these two. One on top is 1 minus x squared minus y squared minus this one, 1 plus y, okay, because the minus sign changes both of those sides, okay? And then the first of these is going to be a dx, and the last is going to be our dy. The dx is going from 0 to twice the 0 to y square root of y minus y squared, and then the other. Now, the 1 minus 1 goes to 0. Okay, so that's out of there. So this is x squared minus y squared. No, I'm sorry. So I'm going to write it as y. Let me rewrite this since I have taken some stuff out of it now. Let's write it as y minus y squared minus x squared. Okay, that's going to be what I'm integrating. Okay, so let me go on and erase all this because I don't have the liberty of having lots of room anyway. So let me, that's y minus y squared minus x squared. Okay, that's what you get by subtracting this one from that one and then rearranging a little bit. Okay? Well, when you do the first integration with respect to x, I'm going to take this 2 and put it all the way on the outside. It doesn't really matter. Just rather than hanging it around any longer, just wait till the very end, multiply by 2. Okay? Let's do the first integration. So it's going to be 2 times the integral from 0 to 1. But this integration, now you're doing dx here. So the y you treat as a constant. That would be yx, right? Next, minus y squared x. What's next? Minus x cubed over 3. And that we're going to evaluate from 0 to the square root of y minus y squared. Okay? And then we'll do our dy later. See, it's going to take some room now. So let's take this, there's the 2, and we're going to do the integral from 0 to 1. Okay, we're going to evaluate this at square root of y minus y squared. Okay, that's going to plug in for the x. So that's going to be y times the square root of y minus y squared minus y squared times the square root of y minus y squared minus, okay, it'll be the thing on the inside, that's when you square the x, times the radical part again, that's the third factor, so that's going to be y minus y squared times the square root of y minus y squared all over 3. Okay? And then when you plug in a 0, all of them go away. And that's why I wanted to use 0, because it makes it so much easier. And this is going to be dy. So I'm afraid I'm going to have to erase even my picture here because I don't have enough room for anything. So let me erase the picture with all of its glorious pieces and parts. Okay. And this is the final part of the integral. Easy said, maybe easier said than done. All right. It's going to be 2 times the integral from 0 to 1. Let's see if we can combine any of these things. Here we have a y times the square root of y minus y squared minus y squared times the square root of y minus y squared minus, and then multiply that, that's y minus y squared over, I'm sorry, okay, all this is over 3, so, okay, let's do this y times that, so it's minus y onto the square root of y minus y squared over 3, and then minus a minus, which is plus y squared times the square root of y minus y squared over 3, and finally your dy then. Okay? Whew. Okay. Oh, whoa! Oh yeah, okay. Works out okay. I was afraid we'd lost everything. Well, this one minus that one gives you 2/3 of that thing. This one minus that one gives you a plus, minus 2/3 of that thing. So we got a 2/3 multiplied by 2 is going to be 4/3, okay, times the integral from 0 to 1 of y on the square root of y minus y squared minus y squared on the square root of y minus y squared. Okay, dy. Okay. Whew. Wow. Not a particularly pretty picture, is it? Let me make sure that everything I've done is correct. Yeah. Here's what this winds up being. If you factor out the square root of y minus y squared, then you have y minus y squared. So when you multiply those two together, that gives you y minus y squared to the 3/2 power. So that's how they write it. This thing, so I'm going to go back and erase because I don't have room to spread it out. Okay. I can just remember and make all the terms work. I think I can. Okay. So it's y minus y squared to the 3/2 power times dy. Okay. Now, now, they do a really handy-dandy little trick on you here. And it's something that's not immediately obvious to me to do. So what I'm going to suggest is that we turn to the back of the book, to our integration table, and see if we have anything like this that we can fiddle with. I don't think we have a big enough. No, we don't. This is not thorough enough. If you had a whoa. Came close there, but not quite. Now basically it's just down to tricks and insight. And I can't tell you an easy way to do this. They just come up with something sort of irritating. They just say, hey, look, that's the same as this, okay? And there is no reason to assume that anyone would realize that's the same as this. And I was trying to think of some easy way to show it, and I can't. They just come up with a term, and they say the 4/3 is out here, and then they say this is the same as 1/8 times the integral from 0 to 1 of 1 minus 2 y minus 1 squared to the 3/2 power. Whoops, that's not what I wanted. Okay. All right. Okay. And then that closes out on a dy. Now, I'm trying, like everything, to think of a nice, easy way to do this. It almost looks like you're completing the square again, and you, in a sense, you really are. And I'm trying to see if that relates any way to this, and it really doesn't seem to. So I don't know. They picked it out. Okay. Now this, if you look at that form, that is in the back of your book. It's the Appendix B on page A3, as if that's helpful. You're integrating something to the tree has power. I think this is correct. I don't see it there either. Yep. A bizarre problem. I mean, you could almost tell it from the very beginning. This was going to be really strange when you have a paraboloid cut by a plane at an angle. It really does come out strange. Okay? And they just off the wall tell you that turns out to be a cosine fourth theta over 2a. When you do 2y minus 1 equals sine theta, that is going to do it for you. So I'm of the opinion, let's not waste any more time on that. I will do my best not to give you one that is that complicated. Okay. I think that was the penultimate one in that section. So let's just leave it there. You can follow it in the book if you want to, but I'm not going to take any more class time trying to reproduce that when they skip so many steps. It's all correct, but it's a lot of busy work. So let's move down to 986, which is average value of a function. Now it's sort of similar to what we did in regular integration, single variable integration. For a function f in one variable, the average value of f on some interval a to b is the integral of that function from a to b. That gives you basically everything under that curve. Now f of x, I think, has to be positive everywhere, that type of thing. And so the whole area under it and divided by the length under it, and that gives you the average y value for it. Okay? It's sort of like, this is a sum. Remember that an integral is sort of like a sum. You're summing all the f's and then dividing by how long it is, and that gives you the average, how thick it is. Okay? If y is your thickness and x is your length, and this is the sum of everything under there, the area divided by the length is going to give you the height. Okay? So, or the thickness of it. So this is the formula we had before. Okay? Given a function of two variables, you can find the average value of alpha for the plane region R, shown by this definition. If f is integrable over the plane region R, okay, so R is something on the plane down here, assume the xy plane, but it could be any plane, then the average value of f over R is 1 over the area, not 1 over the length, but 1 over the area, times the volume. The double integral over that region of that function, that's the whole volume of it, and divided by the volume, and that's going to be your average, in a sense, your average z value. Where A is the area of R. Okay? So don't think these A's have anything to do with average value. These are the areas, and the average value is that. Okay. Now, Are they going to show the, yes, they're going to show example 6. So let's do it. Find the average value of f of xy, which is 1/2, okay, 1/2 xy, that's your function, over the plane region R, where R is a rectangle with the vertices 0, 0, 4, 0, 4, 3, and 0, 3. Okay? Now, they got a picture in the book, but you don't have the book. So let me try to illustrate this. This is not a pretty sight to draw. Okay? And they put it at an odd angle that gives you a little more flexibility in drawing it. I'll try to do what they did. Let's do, this is the x-axis. Maybe a little further down. Something like that. This is the x-axis. Here's the y-axis. Z is going up like this. So you have right-hand rule here. Okay. X is from 0 to 4. Y is going 0 to 3. So here is your rectangle. Okay. 0, 0, 4, 0, 4, 3, and 0, 3. Okay, that's your rectangle, those 4 points. Okay. Now, because your function is 1/2 xy, everywhere on the x-axis, if x is 0, your z is 0. Everywhere on the y-axis, when y is, on the x-axis where y is 0, your function is 0. Everywhere on the y-axis where x is 0, your function is 0. Okay? But then it takes off and blows up, and this corner up here is 4, 3. And if you do that, 1/2 of 4 times 3 would be 1/2 of 4 is 2, and 2 times 3 is 6. So you got 1, 2, 3, 4, 5, 6 here, and this would be the point something like that. All right, Terrell showed up today. Good deal. Now, I held off making any announcements until I got as many people here as possible. And since I'm going to wait and see if anyone else shows up. What is it now? Just a little after 1, and we go. So we got about 45 to 50 minutes to go. Close to 50 minutes to go. Okay, so before the end of the time, remind me to stop and talk about how we're going to finish the term. Okay. So at this point 4, 3, if you plug 4 in for x and 3 in the y, you're 6 up. 1, 2, 3, 4, 5, 6. So that's somewhere about here. So it's going down to here, down to there, down to everywhere along there. So this is sort of how it's looking. So we want the average value of this function. Okay, and these are all curved lines. I didn't draw them as if they're curved enough. Okay, but they're curved lines going up pretty abruptly there to that value. Okay, so what's going to be the average value? Well, just looking at it, it's going to be closer to 1 or 2 than it is anything above 3, because you have very little volume up there. Okay, so first, okay, the average value, let's write that down. Average value is equal to 1 over the area times the integral of your function, okay? So, yeah, the double the area over the region R, that's the region R, function of x and y dA. Okay, now, look at that. Oh, yeah, it's coming. So forget my picture. You're going to see it in a minute. Okay. So, it's a simple area down here. What is the area there? 4 on x, 3 on y. The area of the plane down there. 4 times 3 is? Second? 12. Okay, so the area is 12. So we got the first part of it right there. Okay, so that's equal 1 over 12. Okay, now we're going, this is a simple integral. Everything's a rectangle, so it doesn't really matter which order you do because your function is, and that's a 1/2, so I'm going to pull the 1/2 out and make this 1 over 24. Okay, and this will be x times y, and it doesn't matter whether you do dx and dy or dy and dx, but whichever one you do, get your x to go from 0 to 4, and your y is going 0 to 3. Okay? And it really doesn't matter which one you do first. So this is 1 over 24, okay, because the 1/2 we pulled on the outside. This will be from 0 to 3. We're going to wait and do that later. Let's do this integral first. What will that, what's the antiderivative with respect to x of xy?
Since you have y, we can consider the xy. Is that x squared y?
X squared y over 2, because you treat the y as if it's a constant. So that's some constant times x, and the derivative, antiderivative of x is x squared over 2. So that's over 2. Right? So it's y x squared over 2, or x squared y over 2, evaluated from, and remember these are x values, 0 to 4, and then we're going to do our dy later. Okay? So I'm going to pull that over 2 out too, so now we're up to 1 over 48, integral from 0 to 3. I'll come back and do that in a minute, but let's evaluate. This is x equal 4, so that's 16 times y, and minus 0 times y, right? Okay. I'm sorry, yeah, 0 times y. Second? Yeah, that'll be the 0. So this will be your last dy. Well, let's pull the 16 out, and that now makes it a 1/3. Okay? So this will be 1/3. Antiderivative of y is y squared over 2, evaluated from 0 to 3. So this will be 9. You plug the 3 in for y. That would be 9/2 times 1/3. That would be 1/3 of 9/2, which would be 3/2. Okay, so that we say is the average value. Yes, that's what they got to. Okay. Now, we may have done orders a little differently, but we still got the same thing. Does that make sense? All right. Homework exercises in 14.2 would be 3 or 5. They're both at Calc Chat. 3's at Calc View. Any of the odds 9 through 11, they're all at Calc Chat. Any of the odds 13 through 19, they're all at Calc Chat. 13's at Calc View. Any of the odds 21 to 25, they're all at Calc Chat. 23's at Calc View. Do 27, it's at Calc Chat. Any of the odds 29 to 33, they're at Calc Chat. Do 35 is at Calc View, Calc Chat and Calc View, and then either 37 or 39 They're both at Calc Chat. Then do any of the odds 40, either 41 or 43. They're both at Calc Chat. Now it says you need a computer algebra system. If you do and don't have access to one, forget about it. But if you can figure it out without it, that would be fine. Any of the odds 45 to 49, they're all at Calc Chat. Yep. Any of the odds 51 to 55, they're at Calc Chat. 51's at Calc View. Try doing 57, that's an average production problem. And then if you want to explore some concepts, 59 would be okay too. There is some probability, what they call joint density function. You can do either 61 or 63. 65 is a proof. You can do that if you'd like. They're all should be at Calc Chat. 67 is an approximation problem. You should be able to do at Calc Chat. You should be able to do. It's also at Calc Chat. There's a true-false 69 that should be at Calc Chat. A maximizing problem at 71 is okay. There's a 73 is an average value problem like we just did, and then 75 is one of the Putnam challenges, and you don't have to do that unless you really feel hankering to do so. Now, I kind of arbitrarily decided to skip 14.3, okay? It's good stuff, important stuff, but it's, if you ever need it, you'll go over it again anyway, and I don't see any reason to take up the time in this class. I think the more important part is coming up in 14.4, which is center of mass and moments of inertia, and I think these are things that, aren't both of you pre-engineering majors? Are either of you mechanical engineers? You're what? Electrical. I'm not sure you're going to have these either, except, well, let me say it this way. I think all engineers have to take statics and dynamics. Whether you use it in engineering or not, you're going to have to take it. And in statics and dynamics, I almost guarantee you, you're probably going to run into some centroid problems, centers of mass and moments of inertia, because that's what they do in there, okay? So, but before we do that, I'm sorry, I forgot. Let me erase this so we can see how they did their problem, this example 6. The area of the rectangular region is 4 times 3, which is 12, exactly what we did. Okay, so there's the area that takes care of that. The bounds for x are x going from 0 to 4, for y are 0 to 3. We solved that. Those are going to be the limits on your integral, ultimately. So the average value is your 1 over a times the volume under the curve over that area. Well, the dA is dx times dy. Your region is going from 0 to 4 on x, 0 to 3 on y. So if you did dx dy, that would be the order that you would do that. And the function is 1/2 xy. Okay? So, your area was 12, so it's 1 over 12. And then your integral from 0 to 4 for dx, and they did it in reverse order, 0 to 3 for dy, didn't matter, 1/2 xy. Okay? What I did was go and pull that out and make it 1 over 24, just the xy. I don't know if they're going to do that or not. No, they leave it in there. Okay? And when they integrate with respect to y, that gives a y squared over 2, which makes a 1/2 become a 1/4. Okay, the x is not integrated because it's counted as a constant. Where you plug in, remember, the first integral was y, So plug in 3 for the y, and you get 9. So it'd be 9/4 x minus 0. So you don't have to worry with that. And I would pull the 9/4 out. Let's see if they do. Yes, they do. And then do the integral from 0 to 4 of x, which is going to be x squared over 2. Evaluate it from 0 to 4. And there's your x squared over 2. Now they simplify this. 3 will go into 9 3 times, 4 will go into 12 4 times. That's 3/16. So that's where that came from. 1/2 x squared is there. Plug in 4 there. And 4 squared happens to be 16, so they're going to cancel out. So that leaves you 3x. So that's a pretty straightforward way to do the problem. Or you could do it that way. Evaluate that. 16, half of 16 is 8, and to 3/16 of 8 is 3/2. All right. Either way you want to do it. Okay. All right. Now, we're through with that section. Let's go to, like I said, we're going to skip the polar coordinates for now, and we won't have time for it. Let's go to 14.4. And we probably aren't going to have time to finish this, but let's do as much as we can. All right, slideshow from current slide. Okay. So we're still doing multiple integration, and this is another application of that, center of mass and moments of inertia. Okay? Now, I can't remember. Do y'all do this in physics? Moments of inertia?
We haven't touched that. No.
Yeah, I don't usually teach it either, but like I said, statics and dynamics is a real good chance you will. So let's do it. Find the mass of a planar lamina. I don't know if y'all remember what they mean by a planar lamina. Planar means it's in a plane, and usually a lamina means it has a constant density. The problems I've seen here, they have variable density. So I guess they're still calling it a lamina, but most of the time I've always counted that as something with a constant density. We'll see. Using a double integral. So we're going to find the mass using a double integral. We also find the center of mass of a planar lamina using double integrals. And finally find moments of inertia using double integrals. Okay? So let's start with the mass part. If the lamina corresponding to a region R, shown in this here, has a constant density rho. And that's what most of the time we think of as do it. Okay? So notice what's happening here. You have a g of x up here, g2 of x up here, g1 of x down here. Those are the bounds. g2 of x is always greater than or equal to g1 of x. Okay? So that's going to be our width, you might say. The length is going to be x going from A to B. So ultimately, your last integration is going to be the x, dx, because that's going from A to B. Your first one, your dy, is going from g of x, g2 of x, g1 of x, and g2 of x. That's going to be the length there. So the mass of the lamina is given by your density, rho, times the area. Well, the area is that's the density times this double integral. Okay? And they didn't take it one more step. And why in the world they would put the rho back inside? There is a reason to do that. And it's a little bit of a dumb reason, but it is. What if that wasn't a constant density? Then you bring your rho inside and integrate with respect to x and y there. But they told you it's a constant density, so leave it on the outside. There's no reason to bring it in. And you wouldn't bring it in. There's no reason to. Leave it on the outside. Okay? So the outer limit, this dA, is going to be basically a dx and dy, but dy then dx, because the last one's going to be x, and this is going from A to B for the x part, and it's going from g2 of x to g1 of x on the dy part. Okay? So that's how you would set up your integral. If not otherwise stated, a lamina is assumed to have a constant density. We will extend that definition of the term lamina to include thin plates of variable density. So there they did it. Up till now, that has been a constant density. Now they're going to include thin plates of variable density. Double integrals can often be used to find the mass of a lamina of variable density, where the density of xy is given by some density function, rho of xy. The definition of the mass of planar lamina of variable density is rho is a continuous density function. It can't have any holes or gaps or discontinuities in it. A constant continuous density function on the lamina corresponding to a plane region R, then the mass M, the total of the lamina, is given by the rho of xy is inside now. That's just some function of x and y. And you have your region that you're integrating over times the area of that region, the incremental area, which usually is a dx dy. Now, of course, if you use polar coordinates, that could be a RD theta. You could do the things that we skipped in the last section. So here's example 1. Let's see what we can do with it. Find the mass of a triangular lamina with vertices 0, 0, 0, 3, and 2, 3, given that the density at xy is rho of xy is 2x plus y. All right. So, let me get my pen set up. Okay. Now let's go back and review. Here is your mass function. Okay? Now, your region here is the region in the plane. Okay? So we're going to have to deal with that. So let's deal with the, I don't know if I can draw it and have it make sense or not. Let's just do it in the xy plane. Okay. 0, 0 is one corner. 0, 3 is the next corner. And, whoops. And 2, 3 is the next corner. So here is our triangular region. This is x, this is y. Okay? That's the triangular region. 0, 0, 0, 3, 2, 3. Okay? Now, imagine this down here, okay? And then you're going to integrate that function, your density function, over that incremental area, okay? Now, it just looks to me like it would be better to ultimately end up with the dy's going from 0 to 3. Yes, sir. Second? No, I mean, this is your class. Okay. You only got a minute or two? Okay.
I'm headed to a doctor.
Huh?
I'm headed to a doctor.
Okay. And I take it you want that last test. Is that right? Did you got the one before that?
I have test 3.
Okay, okay. Now, here it is. Yeah. You're going to have to go back and listen.
Yes.
Terrible thing to do, isn't it? That's what I was looking for earlier. That's from my other class. Could not find my master. Okay, there it is. Now, you're going to have to go back and listen to see which questions you're responsible for. Let me go on and give them to y'all since I'm saying this to him too. If you have time, I'll go on and talk about end of the term activities. Before we go to anything else, are any of you graduating this term? Yay? Nay? No? Terrell? No. All right. I know you can do number 1 based on what we've done so far. That was from 14.1. Number 2 is also from 14.1. Number 3 is from 14.2. And number 4 is from 14.2. We skipped 14.3, and we're now in 14.4. And I know you can do number 6 in 14.4. And I think by the end of the class today, you should be able to do 5. That's also from 14.4. I don't know that we're going to get into 14.5 or not. If we do, then 7 or 8 may be in the picture. I don't think we're going to get there. We just don't have enough class period left. So basically, 1, 2, 3, 4, 6 for sure, and number 5 will be questionable just a bit. You'll have to listen to the thing to see. Okay? And then 7, 8, 9, and 10 will all be bonus, optional. Only do them if you want to, if you have time, but don't waste a lot of time. I will say this, 9 and perhaps 10, but certainly 9 is done just like 2, except it's a triple integral. So you should be able to get that done. You should be able to figure out that one. And I will say this. I would definitely change the order of integration there for number 9. Because you want that last... No, let me see. I'll take that back. No, you won't need to change the order of integration. Perhaps that's going to be okay. So that may be an easy bonus, number 9. It may not. I haven't worked it out, but it should work just like number 2, or very similar to number 2. Okay? All right. So there's your final test.
Will 7 through 10 be 14.5?
Say again?
Will 7 through 10, will all that be in 14.5, chapter 14?
It's all in chapter 14. Let me give you the sections, because I don't remember exactly. It seemed like I may have skipped another section. No, I skipped 14.3. 1 and 2 are from 14.1. 2 and 3 are from 14.2. Wait. 1 and 2 are from 14.1. 3 and 4 are from 14.2. 5 and 6 are from 14.4. 7 and 8 are from 14.5. And 9 and 10 are from 14.6. So if you have time and effort and stuff, you can try to do those others. Okay, so I'm going to do a little timeout here, and let me go and make all the announcements, because Daniel's here, and let me mark you as here as well. Good to see you again. Okay. So here are the how we're going to wrap this up. Going to get as far in 14 as we can today. That's what we're in the process of doing. Got to remember to put that back where it belongs. That's that. Then, and I'm going to give you, I've already given y'all, anyone else who comes in, I'll give your the final exam to and explain the problems we're going to do. By the end of the period, we'll know how far you can go. Okay. Now, when is it due? If none of you are graduating this term, you can get it to me as late as Friday morning. First thing Friday morning.
This Friday.
No. Next Friday. Okay. Next week is finals week, so it's due in any time next week. Okay. Now, if you get it to me this Friday, that'll be fine too, but you don't have to. Okay. Finals week, get it any time. Technically, this class, since this class starts at 12:15, it would be technically due by Monday at whatever time. I don't remember what time the final would go. 12 to 1:50 or 12:30 to
12:30 to 1:55.
Okay, something like that. So anyway, but you don't have to do that, okay, because you have all week to do it. So so I'll take it any day. Whenever you finish it, turn it in to me. Now, if anyone is graduating, I'm talking to people who may be listening on YouTube. If you are graduating, I've got to have yours by Tuesday morning of finals week, okay? because your grades have to be due in by noon on Tuesday. You folks, it's noon on the following Monday, so I've got plenty of time. But I'd like to have everything in Friday so I can get as much graded as possible on the weekend so I can get the grades in Monday morning, because I have to have them in Monday morning. Okay? Does that make sense? Okay. And have all of you done the student course evaluations? Yay or nay? You have. Excellent. Okay.
I started. I just haven't finished.
Okay. Well, please do the student course evaluations. Oh, looky here. Well, wonders never cease. Okay. Jeremy's here. You heard? Okay. Yeah. Yeah. That's all I had. Okay. All right. I just gave the others the last task because Daniel came in on his way to a doctor's appointment and he had to leave, so I thought since I gave them to him. Okay.
That's the final exam.
Yeah. And y'all help me here because I covered it all up. Does this start? Yes. This is it. First question. That's not it. Ah, here it is. First question. Evaluate the integral from y to pi 23rds. Okay. Yeah. And I was just telling them, and I'll do it again. Okay. Questions 1 and 2 are from section 14.1. And I meant to say this while Daniel was in here. I forgot it. Okay. Y'all want to listen up? Okay. Number 1, I kept looking at that and saying, why is that a single integral? And then I remembered. Notice in that you're integrating with respect to x, but you have y both in the integrand and in the limits. So guess what? You're going to wind up with y in your answer. And it may be a fairly complicated answer, so get ready for that, because you see the only thing with x's in it is your sine cubed 7x. So that's the only thing you're integrating. You count cosine y as a constant, right? And then you plug in, when you do the antiderivative of that with cosine y being a constant. So your answer, I'll guarantee you this, every term in your answer is going to have a cosine y in it. It's got to. It's a constant, okay? And you may have multiple terms there.
The fact that they have y to pi 3, can I just replace the y with 0 for now?
No. No. Y is y. Okay? What the dx at the end means, this is going from y equal x equal y to x equal pi 23rds. So you just, that is a value for x. You evaluate when you do the integral of sine cubed 7x with cosine y being a constant, okay? When you do that integral, okay, of sine cubed 7x, okay, whatever it turns out being, you may have to look in the back of the book at a table or something else, wherever you go to do that. Then you plug in first in the upper limit, x equal, in those answers, x equal pi 23rds, which is a weird number too. But then you're multiplying by 7, so it's going to be 7 pi 23rds, or whatever, you know.
Can I decimal that? Can I turn that into a decimal?
Say again?
Can I turn it into a decimal?
It's better just to leave it in terms of thing, because you're going to have variables in it anyway, right? So why don't you leave pi's in it anyway? It's easier than trying to punch all those numbers in, okay? You can if you want to, but it's just going to make it a lot harder. But then on the bottom side, when you do the minus on the second part, you're going to have y's in there, where you have a sine cubed, or whatever your antiderivative of sine cubed 7x is, you're going to have y's instead of the x's, right? And then, of course, the cosine y is going to be in there forever because that's just a constant, okay? All right. Anyway, that's enough hint there, I think. Number 2 is also from 14.1. 3 and 4 are from 14.2. We just did that finished that section. 5 and 6 are from 14.4. We're skipping 14.3. 7 and 8 are from 14.5. and 9 and 10 are from 14.6. And as I told the others, number 9 works just like number 2, okay, except you do a third integral. Okay? I think you'll find that maybe helpful, hopefully so. Okay? Now, the ones you're required to do are 1, 2, 3, 4, and 6, because we're doing ones like that. If we get far enough along to do center of mass, you can also do number 5. Other than that, the last 4, 7, 8, 9, and 10, and possibly 5, if we don't get far enough along, those are ones that are completely bonus. You can try them. If you get them right, they're bonus points. If you get them wrong, they don't hurt you. If you skip them, it doesn't hurt you. Okay? Got it? Okay. Now, let's get back to 14.4. All right. We're doing this example 1. Now, we're doing a thing here. And again, they left off the little rectangle here. I'm just drawing it because they did it before. Okay? So what is your rectangle here? You basically need to have the equation for this line, right? And the equation for that line is, if I'm not mistaken, let's see, y is equal to 3/2 x, 3/2 x, right? Isn't that this line here? It's going from 0, 0 to 2, 3. Let's plug in a 2 here, and you get y is equal to 3. That works. Plug in a 0, you get that. So yeah, that's the line that is there. Okay? So your ultimate, your first integral, innermost integral, is going to be from 3/2 x to 3. Y going from 3/2 x to 3. Okay? And then you'll do your x from 0 to 2. Okay? So, the mass of the triangular lamina, your innermost function is going to be from 3/2 x to 3. Y is equal to 3. Y is equal to 3/2 x here. So this is your dy's. Okay? Your outer one, the x is going from 0 to 2. So your dx comes last. And then what goes in the middle? 2x plus y. So you see how to set these up? Now, that would have been the same as if the function up here would have been, in the z-plane, would have been z is equal to 2x plus y. Only now it's your density function is 2x plus y. So it works just like the other things did once you figure out the order to do them. And I think that should work. So let's try it. Let's do the integration. Leave the last one till last, okay, the outer one till last. And let's integrate the inner one. And we're only doing dy. So what is the antiderivative of 2x dy? Anybody? 2x dy.
That's going to be 2x dy. I mean 2xy.
2xy. Okay, you count the 2x as if it's a constant, and you're integrating a constant times y, dy. That would just be y. Okay? Sorry, that looks like a G. Okay? Got carried away on my writing. Okay. And then, the antiderivative of y dy. Say again? Antiderivative of y dy. No? y squared over 2, okay? Because if you take derivative of that, you get y. If you take derivative of this with respect to y, you get 2x. So you see?
Oh, I see.
Antiderivative does it backwards, okay? Now, you're plugging in here 3/2 x and 3, but these are y values. If you need to write them, do that. Whatever this is, those are the y values. So this is what you plug in for the y. And then you have your dx out here that we'll deal with later, okay? So that you're going from 0 to 2. Now you're plugging these in for your y. Do the upper one first, and that would be 2 times x times 3. That's 6x, right? Right? Plus, plugging in 3 for y, that would be 9/2, wouldn't it? There is no x in that one. Minus plugging in these for your y, okay? So you have 2 times x times 3/2 x. Well, 3/2 times 2 would be 3, so that would be 3x squared, right? But it's minus because it's on the bottom. And then it's also minus here, and this will be minus, and plug in 3/2 x for y there, and 3/2 x, or let's do it 3x over 2. That would be 9x squared over 4 over 2 would be 9x squared over 8, right? Yay or nay? Okay. All right, so that's what you have here. And times dx. Okay. Before we go about doing anything with that, let's combine like terms, so to speak. Okay. You have 2 squared terms here. Let's get them both over 8. So that would be minus 24x squared over 8, right? Putting this over 8, that would be 24/8, right? Minus 9, so that would be minus 33x squared. Where am I going to write this? Let me do it up here. The integral from 0 to 2 of, the last part is going to be minus, what did I say, 33? 33x squared over 8. And the first part is going to be 6 times, whoa. 6x, that's just 6x. And that's going to be 9/2. Okay, nothing, no like terms there. Okay, this is going to be dx. So this is the integral in x that we're doing. Okay, and what does that give you? Antiderivative of 6x is 3x squared. Perfect. Okay, antiderivative of 9/2 is x. Doing dx, right? 9/2 x minus anybody? Okay, 33x cubed over 8 times 3. Remember, you divide by your, yeah. So the 3 will go into 33. That'll be 11/8 x cubed, right? Okay. And we're evaluating that from 0 to 2. These are x values now. You plug in x. So 3 times 4 is 12, right? That's the first term. 9/2 times 2 would just be 9 plus 9, right? Yay or nay? Okay. And then when you do 2 cubed is 8, so it'll just be minus 11, right? And that will be 10. Woo! All that, and you just get 10. Let's see what they got. Oh, look at that. They got 10 too. Good for them. All right. Made sense? Yay or nay? Follow all the steps. Any part, I lost you. Lots of potential pitfalls here. You see what we're doing? Let's see if their explanation lends any greater insight or makes it more confusing. So let's see. All right. As shown here, the region R has boundaries. X equals 0. That's not much of it. Oh, x equals 0 is the y-axis. Y is equal to 3 is the horizontal part of there. And y is equal to 3 halves x. Or you could say x equal to 2y over 3, 2/3 y. Okay. Either one would work. But since I came up with that one first, then let's do the this minus that is what I chose to do. The density function is 2x plus y. Okay, which means very low density here. Okay, increasing density as you go up because here your x is 0, but then as you go up you add some y, but then as you go here you're then also doubling as you go this. So your greatest density is over here, your least is down here, and this is in the middle somewhere. Okay? So you don't need to know that, but that's why they shaded it kind of like that, I think. Okay? Therefore, the mass of the lamina is the double integral over your dA, that little triangle part, of 2x plus y. That's your density function. Okay? And then they did the dx first and the dy later. That's what our first inclination was, but it was just so much easier rather than invert and multiply that and did the other. But let's see if it works out the same. Okay? So they did x going from 0 to 2/3 y, because x equals 0 to x equals 2/3 y is what they named that one to be. And then the y is going from 0 to 3. So it should work the same. The way they did it, what would be this first integral here? Remember your dx. What would this be? Say again?
It's going to be 2x cubed. No. 2x squared over 2.
Which is x squared plus
xy.
xy. Perfect. And you evaluate that there. Let's see if that's what they did. They did x squared plus xy, evaluated between 0 and 2y cubed. Okay? Now these are x values here, so you plug in for x. So when you square this, what do you get?
It's going to be y.
4y squared over 9. Right? And this would be
It's going to be
2y squared over 3. Right? Okay. 4y squared over 9 plus 2y squared over 3. Get that everybody's coming out. Let's see what they do so I don't have to do the math. Ha! That's 10/9, okay? Let's see if that's right. Oh, man. 4y squared over 9 plus 6y squared over 9. That would be 10y squared over 9. So y squared inside, 10/9 on the outside. Integrate that from 0 to 3. What's the antiderivative of y squared dy?
It's going to be y cubed over 2.
Y cubed over 3. So you do that and evaluate that from 0 to 3. So when you cube y, you get cube 3, you get what's that? Say again?
27.
27. Yeah, divided by 9. 3 would be 9, and then divide by 9 again, and you get 1. Okay? And then when you put a 0, you get 0, so that gives you 10. Right? And that's how they got it. So theirs may have been just a tad easier in one sense, but they were both pretty easy. Okay? The one sense that really made theirs easier, they had zeros on the bottom both times, so it made the calculation. You didn't have to subtract anything when you integrated. But that's a small price to pay. Okay.
If you have
No. Not if you have variable lamina, and not if your shape is anything different. So if this is going 0 to 3 here, say, and if you went 1 to 5, that same thing.
So
That's very different.
can I shift it from 1 to 3? I mean 1 to 4.
Say again now?
From 1 to 4 instead of 0 to.
Okay. Well, yeah, if you did 1 to 4, you see that's a very different shape up here. You're cutting off this little bit and adding a big part up here. Ooh, very good.
So it's not shifting up.
Huh?
I cannot. I'm thinking of shifting it up.
Okay.
Because if I'm going from 0, it's easier for me to set, so I don't have to the double plug, because I know if when I plug in 0 when I have variable, it's just going to give me 0. But when I have a number, so now I have to add that in there and have to solve that out. So it's to take a shortcut. Can I just start from 0?
You can if you want wrong answers. That's perfectly okay. But if you want it right, you got to obey the rules. You pay the piper, because nature doesn't always give you 0 at the beginning. It may be starting somewhere else. Okay. Now, your shortcuts have to be justifiable shortcuts. If they are justifiable, it's okay to do. But like if it's okay, remember one that we did a short time ago was a circle, but it was uniform, and since everything was uniform, I just took half of the circle and doubled it. That's okay. Okay? But if the circle had been located over here, not symmetric here, then it's not the same. Okay? So you have to go with what they give you. Okay? Now, that was example 1. They're skipping example 2. Now, that's finding mass by polar coordinates. Since we skip polar coordinates, is it all right if we skip this one? Yay or nay? Well, it's sort of a moot point anyway, isn't it?
Yeah.
We're out of time. So it looks like the moments and center of mass, you can skip that one too. What was that, number 4? Five, yeah, number 5. So that's going to be optional for you. You should be able to figure it out if you have plenty of time. However, a few of you haven't turned in research papers. I meant to say that while Daniel was here, so he may, I can't remember. A few of you haven't turned in test 1. At least one person hasn't turned in test 1. Let me see. Research papers, I've gotten 3 of the 1, 2, 5. So 2 people haven't turned in research papers. Test 1, one person hasn't turned in test 1. Okay. Test 2, 2 people haven't turned in test 2. Test 3, 0 people have turned in test 3. And test 4 you just got today, right? All 4 of you got it. Are any of you likely to see Justin?
No, I have a class with him. But
Okay.
I don't know if he's going to be in there or not.
Okay. Now, there was something I gave Justin that I was checking to see if, because you weren't here Monday, were you?
No.
Okay.
If it was the,
Did you get test? Yeah. Oh, okay. Test 3, if you remember, when I gave it to you, I only had the first 6 questions done. And I gave him the last 4, and I had them to give to you too, and I've got this upside down. So let me turn it over. Okay. Did you get test 3?
Yes.
Oh, you did.
Okay, yes.
Yeah, and all 10 questions, right? Yeah. Okay. Okay. I knew there was something else. Test 3. Test 3. Oh, man. There's test 2. Here's test 3. That's the one I gave you. Okay, here's yours. All right, remember I gave you the first 6. Well, when I retyped it and everything for Jeremy, to make it look nice for Jeremy, I put it on 2 pages, so number 6 showed up here. So that's the same as your number 6. Here's 7 through 10. So you don't have to do number 6 for once. Either on the other page or this page. Don't do it both.
If I heard you gave out the answer key too, I'll take that as well.
Okay. Yeah, I'll give you the same one I gave everybody else. There it is. Okay. You got it? Good. I'm so glad. All those have been given now. Okay. Please do your student course evaluations and get me everything. Remember, any research paper after today is going to be losing points. So the sooner you get it to me, the better. If you can get it to me anytime today before I leave at 4 o'clock, then you don't lose points for today. Okay? Good deal. And the other tests, get them to me sooner rather than later. Okay.